Avogadro's laws. Let's do this. So Avogadro's law, there's no calculations involved, but what Avogadro's law talks about is the volume of gas in relation to the moles of gas. And so great example here is a balloon. This is the best example I can give you. So anytime you take a balloon you get out of the bag, it's flat, there's not much gas. So it's small, there's not much volume in there. Now, as soon as I take a breath of air and I blow into the balloon's going to expand and get larger. Now, obviously, if I keep on blowing air into the balloon, well, the size of the balloon is going to get bigger and bigger and bigger over time. Now, where Avogadro's law comes into play is it says that the volume is proportional to the moles of the gas. So as your moles of gas increase, so does the volume of the gas. All right, so they're proportional to each other, and so that's a good example of trying to understand that in terms of, as I look at a balloon, as I put more air in, its volume gets larger until a point of where it blows up, and at that point it's going to hurt your face because it's going to pop you. So Avogadro's law, that's all we have to do with that. There's no calculations involved. What that does do for us, it gets us into the ideal gas law. The ideal gas law is one of the most famous and popular gas laws that has been written. And so ideal gas law is actually coming from these individual gas laws that we've looked at already. Boyle's law, which dealt with pressure volume, Charles' law that deals with volume and temperature, and now Avogadro's law that deals with volume and moles. So the equation that comes up here is this one here, all right? So I want you guys to write that equation down if you're taking notes. PV equals nRT. P stands for pressure, V stands for volume, N stands for moles of gas, T stands for temperature in Kelvin. So again, P stands for pressure, and the pressure is in atmospheres. V is volume, and volume is in liters. N is moles of gas. T is temperature in Kelvin. Now R is what we call the universal gas constant. And R is 0.08206. That's this numerical value. Now R has all the units that you see in the gas laws, or in this particular case, the ideal gas law, which is liters times atmospheres per mole times Kelvin. So this here is a number that you need to memorize. All right. So obviously this all ties into the PV equals nRT. So the ideal gas law is a very important equation. How many have heard of the ideal gas law in a different class? Anybody?
I have.
What do you remember much about it? Is this what you remember about it?
That's basically it.
Okay. All right. So with the ideal gas law, all right, just doing a simple problem here. All right, we have a problem where it says, what is the pressure in atmospheres exerted by a half mole sample of nitrogen gas in a 10 milliliter container at 298 Kelvin? So what we have to do is we have to solve for pressure, okay? So pressure is our unknown variable here. So our volume says 10 milliliters. the moles, all right, what did I tell you moles were here? All right, half a mole sample. This is for nitrogen. And then the temperature was what? 298 Kelvin. All right, so we have all the pieces here. So what we do is we just plug this in. So we have the pressure times the volume. Now this milliliter is converted into liters. So divide by 1,000. And so that's their volume in liters. So always make sure your milliliters get converted into liters for the ideal gas law. And your moles is half mole times R, which is 0.08206 liters atmospheres Kelvin. And then we have your temperature, which is 298 Kelvin. All right, so in order to solve for pressure, we're going to divide by the 0.01 liters to the other side. All right, so there's our volume. So this cancels out here. So all we do now is take your calculators, use parentheses on top. You're going to type in parentheses 0.5 times 0.08206 times 298, close the parentheses, divided by 0.01. And what we end up with is 1,222.694 atmospheres. All right, your liters will cancel out, your moles are going to cancel, and your Kelvin's going to cancel with the units on R. So that leaves you with the units of atmospheres. So that's a short example of how to use the ideal gas law. And so the other thing that you have to look at here are significant figures. So looking back at the problem on the handout here is half moles, that's 1 sig fig, 10 is 1 sig fig, and then temperature is 3, but that's, so basically our answer needs to be one significant figure. So what you could do here to make that 1 sig fig is round down to 1,000 atmospheres. All right, so, and I don't normally suggest doing that because you throw a lot of error into the number. 1,222 atmospheres is a whole lot more atmosphere. So there's a big difference between 1,000. It's kind of like looking at your tires. You have, 15 psi versus 32 psi. If your tire's at 15 psi, it's pretty much flat on the ground. But if it's at 32 psi, it's very solid and rigid. All right, so it's like drilling a basketball. So just to give you an example, that the 200 atmospheres is quite a big difference. So rounding down is actually going to introduce a good bit of error, but we have to in our case because our least significant figure is the 0.5 moles, which is sig fig. So we kind of have to in that situation. So, but that's a good example. So another example could be where we take the same type of information, but instead of given the moles of gas, so let's say we were given 35 grams of chlorine gas into the mixture. So we're going to keep the same constant there. So the temperature was at 298 Kelvin. The volume was at 10. I'm going to put this at 3 sig figs this time. So 10 milliliters. What is it? So we don't know N. We're going to figure that out. We don't know pressure. Our goal is going to be to solve for pressure. So N is what we're going to look at right now. Okay, so what we do know is we have 35 grams of CO2. So what we got to do with this is you got to convert your grams of CO2 into moles of CO2 by dividing by the molar mass of CO2. To do that, we take 35 grams. The molar mass of one chlorine is 35, so that means that the molar mass of chlorine gas is 70 grams per mole. So we're going to divide out 35 divided by 70. That's going to give you, son of a gun, look, it's going to give you a half a mole. We're right back where we started here in this problem. So we have our moles here, which your moles are equal to half a mole. All right, so we don't even need to do anything else with this problem because our problem is set up already here. We would end up with the same answer. Now, so the pressure here was what, 1222.694 atmospheres. The difference in this answer compared to the other one is now this answer is actually going to be 3 significant figures. All right, so we know that our answer was 1222.694. How would we go about getting significant figures to be correct here? Well, there's not an easy way to do this. All right, we could take the 1,200, and one way of doing this is just writing it as 1,220. So just rounding down to this. So that number is 3 significant figures. Another way you could write this is 1.22 times 10 to the third atmospheres. So both of these ways are okay to use. I would think that most students would tend to stick to doing this because most students don't use scientific notation in normal day. So we have 1,220 atmospheres for our answer here. So that's a lot better answer than what we saw previously over here because we only had one significant figure. I can handle losing to an error of 2 atmospheres because, well, 3 significant get is a whole lot closer to what the actual answer is supposed to be in comparison to what we saw in the first example with 1 significant figure. So this is a little game of just making sure you understand how to do the calculation and then paying attention to the significant figures as you do that calculation. So, all right, are there any questions on that? Does everyone understand that? At least make a comment in the chat box so I can see what y'all are thinking and knowing if you have any questions or anything. All right, good. All right, so moving forward here, we are going to get into we have these other 2 equations here we got to work with. This is still dealing with ideal gas law. So with the ideal gas law, you can also focus on density and molar mass of a gas. In fact, one of our experiments is going to be calculating and determining the molar mass of an unknown gas. That's actually something we're going to do a little bit later down the road, not too far away, but we're going to get there. So for now, let's look at the gas law again. So PV equals nRT. And so what our goal here is to include and solve for molar mass. Now, what you need to remember about molar mass is equal to mass over N, which is the same as grams per mole. All right, so that's nothing new. It's just writing it out a different way. So mass over N. Now, if you notice that in the ideal gas law, you have the variable N a part of the equation. If you look at here, we have N a part of this equation. So what we do is we're going to rearrange this. We're going to rearrange and solve for N. So doing that, we just crisscross. So you have N is equal to mass divided by the molar mass. So now that we have our relationship for N, so we have N is equal to mass divided by molar mass. So now what we're going to do we're going to substitute N for N. Okay, so we're going to substitute this back into the ideal gas law. So now what we have here is the PV is equal to mass divided by the molar mass times RT. And I'm just going to put that in parentheses there. So if we want to solve for the molar mass, we need to rearrange the ideal gas law. Sorry. So here we go. So we have the gas law. So what our goal here is rearrange and get molar mass by itself on the outside. So what we can do here is, in fact, this is real easy to do. We just crisscross these out. So you just flip them around. So you have molar mass is equal to mass divided by PV times RT. So here we have our equation that solves for the molar mass of a gas. Okay, so you can do this. Now, earlier in this, I'm gonna go back in just a second. I just want to bring this up. So earlier we had a problem. Where we were given the mass of chlorine gas, the temperature, the volume. We were asked to solve for the pressure. Okay. So now what we're going to do is we're going to take that same information. All right. So we're going to solve for the molar mass of chlorine. All right. So our pressure was 1220 atmospheres. The volume was 10 milliliters. The temperature was 298 Kelvin. All right. And then let's see here. Our mass was given to us at 35 grams. And then what else do we need here? So our goal here is to solve for molar mass equal to. So our goal, so we need to figure out the molar mass of chlorine gas given the information. All right. Any questions before I move on here? So we're going to utilize this equation here. So molar mass is equal to mass, which was 35 grams, divided by pressure and volume. So the pressure was 1220 atmospheres. We're going to multiply that by the volume. Now, keep in mind that this is in milliliters. We need to convert this into liters. We've done this, so it's 0.0100 liters. And then we're going to multiply that by RT. So R is 0.08206, and then we're going to multiply that by the temperature, which was 298 Kelvin. So just kind of in your calculator, what you can do is you can take this. So I'm just going to tell you what I'm going to type in. I wish I could. Maybe I'll just write it out here for you. So in my calculator, what I'll do is I'll have 35.0 divided by 1220 times 0.01 multiplied by 0.08206 times 298, and then I'll hit enter. Okay, so type yours in your calculator the same way I have it there, and we should end up with the answer what we're looking for. All right, and so if you do this correctly, what you end up with is 70 point, and I'm just going to write everything down that I see in my calculator. So that's your answer, but that's not corrected to sig figs yet. So what we need to do now is make that correction factor here. So 3 sig figs, obviously. So this will round to 70.2 grams per mole. So that's the answer for our problem. Any questions on that? Does everyone follow that? Does everyone understand what I just did there? All right, good, good. All right, good deal. So that's how you solve for molar mass of a gas. Now you also can solve for density of a gas, and we can see that here. But let me go. I want to show you that part here. All right. So density of a gas is we're looking at here. So this still goes back to see here, pressure PV equals nRT. And then PV is equal to mass divided by NW times RT. We just looked at that. Now, remember that density is equal to mass divided by volume. All right, so mass, and that's if you look at the equation here. So what we want to do is we're going to substitute into the ideal gas law. All right, so substitution is the important thing here to understand. Now, what we also need to do is before we do any substitution, we're going to rearrange the equation. All right, so we're going to have pressure times MW, and it's a very simple rearrangement divided by the volume here times RT. So now we're going to move the RT over. So we're going to divide up the RT from this side to this side. So you end up with pressure times molar mass divided by RT is equal to mass divided by volume. And so what we see up here is this relationship that mass over volume is equal to density. So instead of writing it mass over volume, we can just have all this equal to the density of the gas. So if you ever need to solve the density of a gas, this would be the equation that you would use to do so. And so now, how often do we do that? I don't know, it depends on the question. I can't answer that. But what I can say is that you've got 3 different gas laws. You've got the ideal gas law. You have the gas law that solves for the molar mass of a gas. And then you have the equation that solves for the density of the gas. So there's 3 different versions of the ideal gas law, but they still follow the ideal gas law equation, which is PV equals nRT. It's just a simple rearrangement of that. And so, let's see here. All right, so yes, here is the other equation. All right, if you write that down, that's great. So all I got to do is just fill in the blanks here. So you've got the first equation we just looked at. Now we have the second equation, which you can input here. So ideal gas law is a very important equation because we use it for a lot of different things. We can use it to solve for molar mass of a gas. We can use it to solve for the density of a gas. So, any questions on that? It's just a matter of inputting the numbers if they give you numbers to calculate those. We did one example with the molar mass of chlorine gas. We could do another one involving the density of the gas. Now, I do want to make a comment here, is that the density of a gas has units of grams per liter. So it's a little different than what we're used to doing. So make sure you write that down in your notes, please. Are there any questions? Are y'all sleeping today? Okay, good, sir. Thanks, Cassandra, for answering me. All right, let's move on in. That makes me feel a little better now. Molar volume of a gas. This is tying into the gas stoichiometry worksheet. So again, if you come in a little bit later, there's a handout online. All right, so if you look at the Moodle page, you'll find that there's one folder, but then there's this worksheet here. So this is the worksheet I'm talking to you about. So what we're getting ready to do is, with the molar volume of a gas, it actually ties into this worksheet and using gas stoichiometry. So gas stoichiometry is just basically utilizing the mole ratio. All right, so we've talked about mole ratios before. There is I'm pretty sure I made a lecture video on gas stoichiometry, and in fact, we are going to look for that right now. So gas stoichiometry here, where is that at? All right, here it is. So I'm going to pause this. So I'm going to paste this into the chat box. I recommend you guys watch this video. Well, Sydney, keep your microphone off then. Save us all, please. I'm sorry that you have to deal with that. You could just give him Benadryl and put him to sleep, but I don't think that's a good idea. Watch this lecture video that I sent you link to, guys. Do that before Friday, all right? We only have 10 minutes of class. I can't teach it to y'all today. I can't teach everything to you every lecture, unfortunately, but utilize that. All right, that's important. Okay, that'll get you to the point where you can answer the questions that are in that worksheet. All right, in fact, going back here, that's the worksheet. Okay, well, what I do have time to do right now is go over molar volume. All right, so that's what I want to do right now. So molar volume is basically dealing with the fact that you are at STP. So molar volume has a value of 22.4 liters per mole. That's a conversion factor, more or less, okay? So we did talk about this on the first page of this. I asked you to write it down, but I told you we're going to go over it later. So we're going to utilize this now. So if you're given a volume, so let's say that we have 10 liters of gas. Well, we're just using chlorine gas since we've been working with it. So we have 10 liters of chlorine gas at STP. How many moles of chlorine gas are there? I'm just going to stop it there. So how many moles of chlorine gas are there? So what we do is we understand that here we're given 10 liters. So we're given the volume of chlorine gas at STP. Now STP has, so standard temperature is 0 degrees Celsius, which is 273 Kelvin. And then pressure is 1 atmosphere. All right. So where I talk about that is this worksheet, this guide. So if I go back up to the very first page, all right, standard conditions, 0 degrees Celsius and 1 atmosphere. So that's on the first page. I ask you to write that down or highlight it, whichever one. I ask you again to write that down or highlight it because that's important. That helps us to solve for these types of problems. You can't solve with it. You could, and there's actually 2 different ways you could solve for this. So what I'm going to show you is the way that I see students typically do this at. All right, so you're given pressure, you're given temperature, and you're also given volume with 10 liters. So they're asking for how many moles that is in. This here is the ideal gas law. All right, so this is representing the ideal gas law, PV equals nRT. So here we know pressure of 1 atmosphere because it's at STP. If I tell you at STP, I'm not going to give you the numbers. You have to know the numbers. That's why I say that's something you need to memorize. That's why I asked you to highlight it. The volume was 10 liters. The moles, we don't know what that is. That's our variable here. We know what R is. R is your gas constant. R is 0.08206 liters atmospheres per mole Kelvin. And then temperature was 273. Now, so what we got to do here is rearrange the solve for N. Okay, so N is equal to, let's see here, 1 atmosphere times 10 liters divided by 0.08206 divided by 273 Kelvin. All right, so plug this in right fast. So I got 1 times 10 divided by 6 times 273. All right, so what I get is 0.446 moles. I'm just keeping this 3 sig figs here. All right, so that's our moles of chlorine gas. All right, perfect. So this is how we utilize the STP, the molar volume. Okay, so this is what we end up with. Now, what I'll show you is that there is another way of using that molar volume. So we were given molar volume of 22.4 liters per mole. So using the ideal gas law, we get 0.446 moles of chlorine. So what we're going to do now is we're going to do this problem again. Yes, I said again. We're going to do it a different way. So now instead we're going to do 10 liters. We're going to use this molar volume. What we're going to do is going to divide by the molar volume. So we're going to divide by 22.4 liters per mole. So the liters cancel out here, and you're left with moles of gas. So you can utilize this whenever you know that you're at 20, when you're at STP. All right. So, and that's the important thing here. Now, when I do 10.0 liters divided by 22.4, I end up with 0.446 moles for my answer. All right. Now, if I go back down and look at the ideal gas law, son of a gun, look at that. We have 0.446 moles of chlorine gas for the ideal gas law, and we get the same answer utilizing the molar volume of a gas, which was 22.4 liters per mole. Now, the question is, Mr. Shelton, which way is the best way to do it? Well, I'm going to go with the easy way, man. I'm going to say I'm going to divide by 22.4 because I know that I'm at STP. It tells me at STP right here. I know from there that I can use the molar volume of a gas, which is this here. That just takes out a lot of work. Now, if you are a person that you don't want to do it that way, you'd rather do it the ideal gas law, you're going to get the same answer. Is one way better than the other? No. One way is just quicker than the other. So it's not necessarily that you have to do it this way that's quicker. You can use the ideal gas law. If you're happy with it, use it. It's going to give you the same answer. All right. But when we go back and we look at the worksheet, all right, the handout that I gave you, all right, so, and I look at the problems, all right, so now I give you two examples here, and what I show you with this example is that each example tells you at STP. The problem has to say specifically at STP. If it does not say specifically at STP, you never can use the 22.4 liters per mole. You only are able to use this and are allowed to use this at STP. If it's anything different, you got to do it a different way. There's no question about it. So in these two examples, and I'm going to leave these two examples for you to look at over the next couple days. On Friday, when we get back, we'll talk about these two examples and make sure that you are comfortable and you understand it.